Hello, good evening. Please let me know if you can see my screen and if you can hear me well so that I can start the last lecture. So today, as you know, this is the last lecture. Just in case you didn't hear the announcements, maybe from your colleagues, you will have to present your projects on 25th of January. So you'll make the presentations for both projects in the same day. So we will allocate maybe 50-minute slots for the presentations. And remember that the second project has to be submitted by 20th of January. Okay, so this was just a reminder for you. So let's start today's lecture. So today we're going to continue our discussion about unsupervised learning approaches. And we're going to discuss about principal component analysis and another dimensionality reduction approach that is actually more useful in data visualization than actually building a useful representation. So as you recall from the previous lectures, we discussed about two main canonical forms of unsupervised learning. One that involves clustering and another one that involves dimensionality reduction. And we discussed about the clustering approaches in the previous lectures. And today we're going to dedicate our attention to principal component analysis, which is perhaps the most popular dimensionality reduction approach. And then we're also going to discuss about t-SNE. So, of course, there are also other dimensionality reduction approaches. One that is really popular nowadays is to use autoencoders, but this is a topic that is discussed in next year in the deep learning course that I'm also teaching. So today we're just going to discuss about these basic approaches. So first about principal component analysis. So in order to explain this method, we're first going to discuss the intuition behind the approach. Then we're going to introduce the mathematical preliminaries that are required to understand the approach. And yeah, this is the main structure of the presentation for PCA. So the idea with PCA is we have some data set that is represented in a very high dimensional space. So in this case, this is a simple example with a 3D space, but it just illustrates the idea that if data is embedded in a very dimensional space, and if you just pick a random projection of the data set, which is the one displayed here, you will see that actually you will not be able to visualize the organization of the data. So if you try to move around, for example, this data set in a three-dimensional space and try to look for a better angle, you will find that actually there seems to be some organization of the data into 6 classes. So this is the main intuition behind PCA, is to try to find this rotation automatically. So the idea is we want to get a better understanding by looking from an angle that gives us a better perspective. So what we did here manually, let's say, rotating the axis, is actually equivalent to changing the coordinate system. So this is what PCA does, is it applies some transformations on the original coordinate system, such that in the new coordinate system we are able to see the data better, let's say. So this means that actually in the new coordinate systems variance between features is 0, and the axes are orthogonal, so these are not correlated, and the axes explain as much as the variance as possible. And these axes are actually called principal components. So these are the as I said before, these are the directions in which data varies the most. So along these principal components we have the highest variations of the data. So principal component analysis means we try to transform the data in this new coordinate system that that is represented through these axes that are called principal components. Okay, so as I said, we can look at the variance that is explained by each component, and here after we apply this transformation, we can we can see that the first axis, the most important one, explains most of the variance. Then the second axis also explains from the remaining axis, it explains the most of the variance, and so on. So for each axis we start with the highest variance and gradually decrease, but we usually observe that usually a few of the first axes are enough to explain the data. Well, in this case we can see that the first two axes explain more than 90% of the data. In practice, if we go from a higher dimension to two axes, maybe we'll not get 99% of the data, but those two axes will definitely explain most of the data. Anyway, but the purpose here is not to necessarily project or to use only the two axes. We can use more of them, but in practice we do not need to necessarily to visualize the data, so this is not the goal here. The goal is just to reduce the dimensions. So we can go, let's say, from points that are represented in let's say in 500 dimensions to 100 dimensions. I'm just giving a random example here, and if the dimensions with PCA explain most of the data, then if you choose the first 100 dimensions, then you will capture most of the variance in your data. So if you go to 100 dimensions, then in this case you do not need or you cannot visualize. You can still not visualize the data, but the goal is to reduce the dimension and also explain as much of the data as possible. Okay, so this was the intuition. Next, we're going to discuss about the mathematical preliminaries. So we use some concepts from probability theory. So we have a random variable. So this is a variable whose possible values are outcomes of a random phenomenon. So one example is a rolling die. So the rolling die is the random variable. It can have two sources of uncertainty, one that is objective, so this is the result of a random process, and one that is subjective, so this is the result of incomplete knowledge about the variable. Okay, so usually a random variable has an associated probability distribution that specifies the probability of its values falling in any given interval. And a particular outcome of the random variable is called random variate. So this is the result of, let's say, rolling the die. So we roll the die, we obtain one of the faces facing up, and we say that that is the value of the random variable. So the random variate, let's say, is when the die landed on, I don't know, 5. Okay, then we have the expected value or the mean of a random variable. So this is the long run average of its random variates. So in the discrete case, it is the probability weighted average of all the possible outcomes. So for example, for a rolling die, we have 6 possible values from 1 to 6, and all these, so if the die is not if it is unbiased, then the die will have a uniform distribution. So then the the weighted probabilities are all equal, so the average is around or yeah, if you go to infinity, it should be exactly 3.5. Okay, so this is the average of all the possible values. So we will use these concepts in explaining PCA. Then we also have the variance, which is denoted by sigma square. So here we have the notion of variance. So this is the measure of dispersion of random variates around the expected value, so around the mean. And the standard deviation is sigma. So the variance is sigma squared. So it's the square root of so it's the square of the standard deviation. Okay, so the random variable can be sampled together in the same time with another random variable. So we can actually, I think I'm discussing the next slide. So yeah, here we just have two sets of random variates that are sampled together from two random variables. So in the next slide, I think it's the next slide. Yeah. So in the next slide, we will discuss about data samples and the fact that a data sample is like so each feature corresponds to a random variable. So the features are random variables, and the data samples are events. So each event is actually sampling each random variable, so extracting a random variate from each random variable. So it means that we have pairs or actually tuples of random variates that are sampled all in the same time. So here we have two sets of random variates, and we say that so if these are sampled in the same time, then xi corresponds to yi. Okay, so so here we have these discrete sets of random variates. So x and y are just subsets of the potentially infinite population. So the random variable can produce an infinite of values. But in practice, in machine learning, we will use finite data sets. So these random variates form a finite subset. And in this case, for discrete sets, we estimate the expected value or the mean and the variance by computing the mean using the discrete set of values. And similarly for the variance, we use the data set that we have at hand. So we call these the sample mean and the sample variance. So yeah, the sample mean is just the mean of all the sampled variables, and the variance is the difference between each sampled variable and its mean squared, so that we all have here positive values, and these are also averaged by 1 divided by n. And actually here we have a correction for the variance that uses n minus 1 instead of n. So this is called Bessel's correction, which accounts for the biased estimation of the mean. So what this means that, let's say, I don't know, you have this, let's go back to the example with the rolling die. So we know that in theory, the expected value or the average of the rolling die is 3.5. And let's say, so we have a discrete set of samples. So we sample, let's say 1, I don't know, 5 and 2. Okay, so we have 1, 5 and 2. The average should be, so the sum is 8. The average is 2.66. Okay. Did I compute that right? Yes. Okay, so the average, or the sample mean is going to be 2.66. So now if you think about the values that we sampled and this formula here, so instead of using here 3.5, we're going to use 3.60, instead of using 3.5, we're going to use 2.66. And this will actually give us a lower yeah, a lower, or I think it's actually a higher value, I think, for the variance, or a lower one. No, it should be lower. Yeah, the value is lower, and this is because the mean is shifted, so it's not the actual mean of the data. So here, if we use 2.66, we'll have an estimation, an underestimation of the variance. And this is because the mean is estimated from the data set, and this estimation is biased, so it's not the actual mean of the data set. So in order to correct this problem, we divide the variance by this value by n minus 1, which gives us a higher value and accounts for this biased estimation of the mean. So this is called Bessel's correction. In a similar way with the variance, we can also compute the covariance of two random variables. Covariance is the value, is a value that tells us if large values of x correspond to large values of y, and small values of x correspond to small values of y. So if these are correlated, then we have higher covariance, and vice versa. So the covariance has the same formula as the variance. So the variance gives us, if the variance tells us how these values variate with respect to their mean, here we see how these values variate together. So if here we have big differences, and here we also have big differences, then we have higher covariation. If these are negatively correlated, then we'll have a negative covariation. So Okay, I think so. I think the commentaries about the covariation maybe are continued in the next slide. So here, yeah, we just what I mentioned before. So we will regard the data set, so the features, as random variables. So here we have the data samples, which are one example per row, and the features, which are the columns. So here we have first feature, second feature, and so on. So we can regard each feature as a random variable, or actually as a set of random variates that are sampled from this random variable. So each component in our data matrix is a random variate, and the examples are made of n random variables that are sampled together. Okay, so this means that X can be interpreted as a set of m sampling events. So an event is a data sample, and we can compute the sample mean, sample variance, and sample covariance. Okay, so what we do here in order to compute these, we can do it using matrix notation. So we can compute the means for each random variable. So recall that the random variables are on columns. So it means here we just compute the average value on each column, and we obtain this vector denoted by mu x. So this vector is a row vector that contains the means for each feature. Then we compute the matrix x bar, which will help us in computing the variance and covariance. So here we have this is the normalized matrix. So we subtract from each component the corresponding average. So now the features in x bar will all have the mean equal to 0. This can be computed using matrix notation. So we can use matrix computation to obtain this this matrix directly. So this is the centered version of X. We can also consider the transpose of this matrix. So if we transpose it, and if we then multiply it with the centered matrix, so this matrix, this gives us a square matrix with the covariances between all the pairs of random variables from the data set. So we use the same Bessel correction, so we divide this by m minus 1. So m is the number of events or samples from each for each random variable. So this is the number, m is the number of sampled random variates. So then if we apply this matrix multiplication here, we will obtain the covariance matrix. So on the main diagonal, we will have the variance of each variable with itself. Then on the other components, we will have the covariance between every two pairs of variables. So yeah, one question maybe here would be if you can think of a property of this matrix. So try to think of the values that this matrix might contain, and can you figure out if it has any particular property? So this is a question that I will award points for. So yeah, the question is, does the covariance matrix have a specific property? So I'm looking more maybe, from. So I'm not asking about the definition of or what values or what the values mean. It's just an observation maybe. Yeah, okay, so we have an answer. So indeed the matrix should be symmetric with respect to the main diagonal. Okay, so now we can also look, so yeah, we saw how we can compute the covariance matrix. We can also try to give it some interpretation in a two-dimensional space. So here we have some data points that are represented in this two-dimensional space. So here in the first case, we have a covariance matrix that is not that represents two features that have no covariance. So these are not correlated in any way. So since these features are independent, the covariance matrix will look something like this. So of course the variance within with the same variable should be the highest possible. So here we have values close to 1 or exactly 1, and if we don't have any correlation, the covariance should be the covariance of these variables should be 0. In this case, we see some correlation. So for lower values of x, we have lower values of x2, and for higher values of x1, we have higher values of x2. And we also have a higher variation for x1 than for x2. So this explains why here we have the value 1, and here we have a smaller value. So with respect to this highest variation, here we have a smaller variation, and also we have the covariation between these two variables. So in this case, we have again covariance, a high covariance for the second variable for x2 and the smaller covariance for x1. So on this axis we have smaller variation, so this is reflected here. And here we have a negative correlation. So here for small values of x2, so here we have small values of x2, we have higher values of x1, and here we have higher values of x2 and smaller values of x1. And notice that these values also represent how high the correlation is. So here we have a very big correlation. Here we have a smaller correlation. So this is how also tells us how the samples are oriented. And yeah, here we have another example where the variables are not correlated, but on one axis we have a higher variation, and then on the other axis x2. So what we're trying to say through these examples is that the covariance matrix can tell us how the data samples behave on our axis, and we can see on which axis we have the highest variance, or on which combination of axes. So from the covariance matrix, we can obtain our principal components, and we can what we can use here is to use eigenvectors and eigenvalues. So first, we're just going to introduce the notation and remind you about what these mean, what is an eigenvector and what is an eigenvalue, and then we will see how we can use this to obtain these principal components. Okay, so we will use actually later this equation, so which is actually involved in the definition of eigenvector and eigenvalues. So for a square matrix of n by n components, here we have V as a column vector. So we when we multiply the square matrix with the column vector, we will obtain here a column vector. And eigenvectors are the solution to this equation. So when we multiply this matrix with an eigenvector, we will obtain the eigenvector scaled by some factor lambda. So the scale factor of this eigenvector is called the eigenvalue of the respective vector. So this equation can have multiple solutions. So any solution to this equation is an eigenvector, and the corresponding lambda is a eigenvalue. Okay, so what's the interpretation? So when we multiply the matrix X by an eigenvector, it only gets scaled. And also mentioned this. So I also mentioned that we have multiple solutions here. So how do we find the principal components? First, we will start with the conceptual idea and try to explain the algorithm, and then we're going to see that we can do this using also eigenvectors. Okay, so what we started with is to try to find an orientation of or a coordinate system in which the data is keeps most of its variance. So in this new orthogonal system, the data is centered, and also the features are uncorrelated. So the features are orthogonal. Okay, so the mean of this new data set will be 0, and since the features are not correlated, it means that a covariance of any pair of features is also 0. So in the new system, the covariance matrix is equal to the identity matrix. So it has 1 on the main diagonal and 0 in the rest. Okay, so the features of the transformed data set are called principal components. So these are independent, the new coordinate system are called, these are the principal components. And as I hinted earlier, these are sorted in descending order according to the variance. So the first component has the largest variance, then the second component has the second largest variance, and so on. Okay, so so after we compute these principal components, we can discard sum of the dimensions from the end in order to reduce the dimension of the dataset. So the main application of PCA is not just to make this transformation, is actually also to reduce the dimensions while keeping most of the variance in the dataset. Okay, so intuitively, as we described first, we will center the dataset. So it means that all the data points will be shifted such that the average on each axis is equal to 0. So the sample mean of these random variables x1 and x2 will be equal to 0. And then we look for a direction on which we project the data points that has the largest variance. So we're looking for a line on which, when we project the data points, we will obtain here the largest variance. And one idea, one possible solution in order to obtain the first principal component is to minimize the sum of the distances from to the points, so from the line to the points. So if we minimize this objective, we will obtain this this line that has the largest when we project the data on this line, we will have the largest variance in the data points. Okay, so one idea could be to minimize this objective. Then this line will give us the first principal component. Then we will project the data points on the hyperplane that is perpendicular to this principal component, and then we apply PCA in this hyperplane. So in the data points now are projected in this space where they have lower dimension. So the hyperplane has n-1 components. So in this new subspace, in this hyperplane, we will reapply the same algorithm. So we look for the line that explains most of the variance, and what ensures that the two components are not correlated is exactly the fact that we're projecting the points in this perpendicular hyperplane. So when we do this projection, then we make sure that these are not correlated, and then in this hyperplane we search again for the line that that minimizes the sum of distances from the data points to the line, and then we will, in this hyperplane, we will obtain the line that explains most of the variance, and so on. So the process can iterate for a number of components. Okay, so this process is usually easier to understand, and to it's more obvious how we obtain the principal component. So now in this line, in this two-dimensional space, the algorithm is trivial. So we have the first component here and the second component here. Okay, so as I said, the process would go on for multiple dimension, and this process can be quite slow because we have to optimize these sum of distances from the data points to the line in for every principal component. So one remark here is that PCA is not doing exactly linear regression. So recall that in when we discussed about kernel methods, we discussed about linear regression. So it is a fine difference here actually. So here we want to minimize the sum of distances to the data points, while here we minimize the sum of squared distances. So this is one difference, and the second difference is that in this case x1 and x2 are both features, while in linear regression in our graph we used actually there we used the notation x and y, because on one axis these are the features, and on the other axis we have the label. So actually we are just interested in the distance, sum of square distances, only on this axis, which represents the label of the data. So yeah, there are some small differences, but in the end we can still use here convex optimization to optimize using PCA. So this is one approach, and the same solution can be also obtained using Eigen decomposition. So let's also explain this approach in computing PCA, which is more commonly used in practice. So we have the data set X and the covariance matrix denoted by sigma of X. So how do the eigenvectors for this matrix look like? Do you have any intuition? I can provide some hints. So first, consider that the covariance matrix is responsible for the shape of X, what we tried to explain through those four examples earlier. And also recall that the eigenvectors are the vectors that do not change direction when they are multiplied by the covariance matrix. So given these hints, can you intuitively say who the eigenvectors of the covariance, or how do they look like? Okay, I'm not asking about the actual values. So yeah, in this particular case, those are not the eigenvectors. I'm not looking for the particular values. I'm just trying to link them to PCA actually. Okay. It is complicated to say more, because I'm afraid I'm going to reveal the answer. So it's more, maybe it is too obvious. Actually, it's very hard for me to avoid the answer. I'm trying to give you more hints about this. Yeah, of course. So yeah, the eigenvectors are orthogonal, but there is more than that. Okay, so you're just naming properties that maybe can describe the eigenvectors, but what do you actually obtain? Okay, two orthogonal lines, but okay, so how would you name these orthogonal lines in this case? Okay. Okay, so you're getting closer, but you're not saying the the answer. So here what we want to do actually, so recall we want to apply Eigen decomposition as a method for PCA. So okay, I think I'm going to give you the answer. So the eigenvectors are in fact the principal components. So this is what I was looking for. So I wanted you to say, so the eigenvectors are the principal components. Okay, so if you do eigenvector decomposition, the eigenvectors will be the principal components of X. So the eigenvectors of the covariance matrix are the principal components of the matrix X. Okay, so you can obtain the principal components by doing eigenvector decomposition. Okay, and there is actually more than this. The corresponding eigenvalues are equal to the amount of variance that is explained by each component. So how can we compute the principal components or the eigenvectors? We start from the equation used in the definition. So here we have in the formal definition we had the squared matrix A, and in our case the matrix is the covariance matrix, so this is sigma of X. And recall that the equation was A times the eigenvector equal to lambda times the eigenvector. So here actually we put all the eigenvectors that can be solutions of this equation. So we have n of these vectors and we put them all in this square matrix. And we also multiply with the inverse of this matrix to the right, such that the equation from the definition becomes something like this. So V here multiplied with this component, its inverse will reduce from this side, and the right term will look something like this. So in the end, we have this covariance matrix, and we apply eigenvector decomposition in order to estimate the eigenvectors and the eigenvalues. Okay, so the eigenvectors are column vectors. I already said these. This matrix is a squared matrix, a diagonal matrix, where the eigenvalues are on the main diagonal. And here we just apply a matrix decomposition algorithm in order to obtain the eigenvalues and eigenvectors. Okay, so one possible implementation of PCA in Python would be to use this approach. So first, in these lines we compute the covariance matrix. So we take the matrix X as input, we compute the mean for each feature, we subtract the mean and obtain X bar. We compute the covariance matrix bar by multiplying the transpose of X bar with X bar, and then we apply eigenvector decomposition. So we can use the function Eig from the linear algebra package of NumPy in order to compute the matrix V and the lambdas, and these are the principal components, and these are the lambdas. Now what we have to do next is to sort them according to the lambdas in descending order. So this is why here we use minus lambdas, and then we can keep here we permute the data set the eigenvectors in the order of the scale in the order of the eigenvalues. So here we will have the eigenvalues sorted by how much they explain the data. In order to transform the data in the new space, we multiply the original matrix X with the eigenvectors, with this squared matrix containing the eigenvectors, and this will apply the transformation, and we obtain the transform matrix X, and here we will return this matrix. So here maybe what is important to say is that we can apply this approach in actually I think it's in the next slide. Maybe this is just using we can also use the implementation from scikit-learn of PCA, but here maybe it's not really also shown. So here if you want to let's say apply PCA for a dimensionality reduction on some supervised model, so let's say we have a model with a lot of features, and we want to reduce the number of features. So we have to be careful here when we apply PCA because we will apply it on the training data, but we want to apply the exact same projection also on the test data. So the right way to apply PCA on a data set that is separated into training and test. So this is usually done because the test data samples are not available when you train your model in theory. So you can only apply PCA on the training data. Okay, so you want to take this data to reduce the number of features by applying this transformation. So then at test time, you want to apply the same transformation to each test sample in order to make sure that the features represent the same thing. If you do it otherwise, so if you apply PCA on training and then for test data you apply PCA on test data and reduce to 50 dimensions, you will obtain since the data is randomly sampled, you will not obtain the exact same projection. So maybe the features will not the features will not be identical, and you will actually make bad predictions at test time because the features are not the same as those used during training. So it is important to keep this transformation if you want to transform other data samples later. Okay, and here in scikit-learn you can do the same thing. So first you can feed PCA as any supervised algorithm, and once you feed it, you learn the transformation, and then you can transform any data points by calling the transform method. Okay, so you can look at the coefficients of the components and explain variance of each new component, and so on. So yeah, you can look at how PCA works in scikit-learn, and how you can use it. For example, this is a very simple case with a widely used data set of 150 data samples that are represented in a 4-dimensional space. And here, if you just take any pair of features and the corresponding classes, you will see that not any pair of feature will give you a good separation of the classes. So it means that if you want to do feature dimensionality reduction, so if you want to select let's say 2 features out of these 4, if you just try to take any pair of features and use those, you will not be able to separate them so well. But if you apply PCA on the data set, you will obtain this projection, which is gives us a better separation of the data samples according to class. And this is because it explains most of the variance. But remember that PCA does not use the actual labels, so this is just maybe in this case it should happen like this, but it's more maybe like a coincidence. But in general, it doesn't look at the label, so it can be the data can be mixed. Okay, so also if you look at the principal components in this case, you'll see that they explain the first 2 components will explain more than 97% of the data. Okay, so what are the limitations of PCA? So the first limitation is that it doesn't take into account nonlinear correlations. So this data set is just projected in a is transformed, let's say, in this. So the first dimension will be this one. So if you want to project these data points into a single dimensional space, all the data points will be projected on this line. And here maybe an idea or a solution could be to use autoencoders. So because autoencoders make nonlinear projections, so you will be able to learn with autoencoders a nonlinear manifold. So the data points will be projected on this nonlinear manifold, and the manifold can go along the S like this. Okay, and the other thing is that PCA does, as I said before, it doesn't take labels into account. So when it projects the data point, it looks only at the variance. So, and the data samples can look something like this. And yeah, this is also why PCA is not that suitable for data visualization. Okay, so just to make a summary of on PCA. So PCA, as we saw, it transforms a data set into a new orthogonal coordinate system in which the data is centered and the features are not correlated. The directions are called principal components, and they are sorted by variance, such that the first principal component explains most of the data, so it has the highest variance. Usually components with low variance can be removed, making PCA a method of dimensionality reduction. Okay, so the limitations are that, as you saw in the previous slide, that it doesn't deal with nonlinear correlations, so it will not model these, and it also doesn't take the labels into account. So it is an unsupervised method for dimensionality reduction. But okay, this is also valid for the autoencoders. Okay, so next we're going to discuss about data visualization using stochastic neighbor embeddings. And what we want to do here is we have some examples in a set X that are in a high dimensional space, and we want to project this set of examples into a lower dimensional map. So here X is a high dimensional data set and Y is a small dimensional data set that has 2 or maybe 3 components. So we can visualize the data in a 2-dimensional space or a 3-dimensional space, but we cannot go higher than that. So it's maybe an approach that can also be seen as dimensionality reduction, but is not useful for dimensionality reduction. Okay, so the first question is why not just use PCA? So if we try to do this using PCA, we will obtain maybe a visualization that looks something like this. So because it doesn't take into account the labels, the data, so if you want to visualize the data, it will look something like this. So it's not really explanatory. Okay, so if you look at the data without the labels, you will see that it looks maybe just like a cloud of data points without being able to identify any clusters of classes. Maybe we can see this cluster here, but all the others are maybe mixed together here. So it's hard to figure out if there are any clusters or any classes meaningful there. Okay, so we do not use PCA because PCA just projects the data such that the variance is maximized, and the results are bad because PCA does linear projection, and it also tries to preserve the distances between dissimilar points. So it tries to preserve the distances between all the data points. So for visualization, we're not really interested in this aspect. We just want to preserve the distance between very close points, and we do not care about the distance between points that are very far away. So this is an example here that explains why PCA is not really useful. So if we have a data set that is organized something like this, just like a roll, then when we do the visualization, maybe we would like to look at the data to have something like this. So it means that if the points are close together, so in this visualization, 2D visualization, the data points that are close together are still close together in this visualization, but those that are farther apart are really not close together anymore. So sorry, if you look at these data points here, they are actually further apart in the visualization than in this 3D space. So for the purpose of visualization, we are just interested in preserving the distances between points that are closely packed together, and not in distances between points that are far away. So and in the original space, the distance here is shown by this dotted line, and in the visualization, the distance between these 2 points is something like this. So it's much greater, but still the visualization looks better in this case. So this is the intuition why we want to use a different approach, and this is actually the intuition behind stochastic neighbor embedding, or SNE. So in contrast to PCA, it focuses on maintaining in preserving the nearest neighbors in the lower dimensional map. This approach was introduced in 2002, so it's introduced almost 20 years ago, but its updated version that was introduced in 2008 is still used today. So first we're going to discuss about the original algorithm, about SNE, and then we introduce the updated version, which is called TSNE. Okay, so first what we do with SNE, we transform these Euclidean distances between data points into a probability density denoted by P of J and I. So P of J and I, what we want here is to have, if the points are close together, we want to have a high probability, and if the points are further apart, we want to have a lower probability. We model this with a Gaussian distribution. So this probability density is actually a Gaussian distribution. Yeah, so we use the distances as a way to obtain this probability density, and then when we optimize, when we apply the optimization, we want to make sure that these probabilities are for close points are still high, and we do not care about the probabilities of points that are farther apart. Okay, so we use this density probability in the high dimensional space and also in the low dimensional space. So we model the data points with this Gaussian distribution that is given by, so between two points I and J, it is equal to so this is the distance between the points, and as you might recall, this is equal to the RBF function, or the exponential, or the Gaussian kernel. So this transforms the distance, which is between 0 and infinity, to values between 1 and 0. So yeah, so if you remember the exponential function, e to minus x is applying a mirror of the exponential function with respect. So you flip the exponential function with respect to the vertical axis. So then for the value 0 on the x-axis, you will obtain the value 1 for the probability, and for all the other values you obtain so the exponential function, as you go here with the distance towards infinity, you will obtain values that are closer and closer to 0. So this density probability is equal to this let's say probability between x and j, which is normalized by the sum of all probabilities for all the points xk that are different from the point xi. Okay, so we do the same in the low dimensional space. So we have these density probabilities, and what we want to achieve is to preserve the similarities in the data such that these density probabilities will be equivalent. Okay, so to make sure that so to ensure this objective, so we want to preserve the similarities in the data, so we want to make sure that these are equivalent. SNE minimizes an objective that measures the discrepancy between the similarities in the original data and the similarity as in the map. So here the objective is actually the Kullback-Leibler divergence between the two distributions of probabilities. So these are actually expanded and written like this. So these terms are actually the terms that we defined here previously. So this is our objective, and we want to minimize this objective when we compute our projection. Okay, so the Kullback-Leibler divergence is a function that measures how similar two distributions are, but it is not a symmetric measure. So it just tells us if the divergence, so if the two distributions are equal, then we have the divergence is 0, and the divergence can go up to infinity if the distributions are very different. So yeah, for these two distributions, so here we have a binomial distribution and a uniform distribution with 3 bins. So we're just using 3 bins here, and we estimate the distributions of these probabilities using the bins here. So you can see that the divergence between the two distributions is not symmetric, so we obtain different values. Okay, so this gives you a practical example on how to compute this this Kullback-Leibler divergence. So in practice, what we do in order to optimize it or to minimize it is to consider that this is some sort of weight, and this is the error term, and we want to here the weight is actually proportional, so the probability gives us tells us how important is the error. So if the points here are close together, then and in the mapping, if they are farther apart, then we will have a higher penalty, and this is because we will have so let's say if we just have the error terms here, and if we have points that are close in the mapped, so close points are mapped to far points, or far points mapped to close points, we will have a similar penalty. But if we add this weight into account, then if we have for the first case, we will have a higher weight because the points in the original space are close together here. So if they are close together, we'll have a higher weight, and this means that we will have a higher penalty in this case, and a lower penalty if far points are mapped to close points. So this means that by optimizing this objective, we will make sure that close points are mapped to close points, and we do not care so much what happens to the points that are far away. Okay, so we are focusing on preserving the local structure of the data. So by optimizing this objective, we will obtain what we want. Okay, and this is a result on the MNIST dataset with PCA and with SNE. You can see here that the cluster, the optimization produces clusters that are interpretable. So we see here clusters of 0, a cluster of 3s, clusters of 4s, clusters of 1s, and so on. So the clusters are more meaningful. There is still a problematic, so the approach is gives us the result that we want, but the approach is not that efficient in terms of computation. So it's still SNE, it's hard to apply on many data samples and on many classes. So the optimization with SNE is based on gradient descent. So we have the gradient of the objective with respect to the targets. So remember that our targets are the mappings denoted by y of a and y of j. So this is the gradient. The update rule is based on gradient descent with momentum, and the update applies on y. Okay, so we update the embeddings, the y's, the set y, by taking the embeddings from the previous step. We add the gradient with some learning rate, and we also include the momentum term, which is controlled by this momentum rate. Okay, so the optimization is performed using gradient descent, and actually here we have a lot of local minima, so the Kullback-Leibler divergence is not convex. So there are some techniques to avoid the bad local minimum, so which involves combining a gradient descent with large momentum with simulated annealing, which is just adding some random noise to solutions just to explore more of the space. So the algorithm behaves something like in this animation here. Okay, so another important aspect is that a good visualization also requires a good choice of parameters for the learning rate and for the momentum rate. So it's not straightforward to obtain it. And maybe one question that arises is if this algorithm does overfitting. So the answer is yes, but this is not a problem in this case. So maybe this is the only case where overfitting is okay and it's actually desirable. So yeah, I just want to emphasize that in machine learning, the goal is to obtain a model that generalizes well. So we have a training set and we want to do well on the test set. So in this case, overfitting is not desired. In the case of SNE, the goal is to obtain a good visualization of the data. So we are given a data set that we want to visualize, and we just want to do well on this data. So in this case, overfitting is desirable. So we do not care about obtaining high generalization and so on. Okay, so the main problem with SNE is that the points tend to crowd together in the center of the map. So a solution to this problem is t-SNE. So t-SNE is short for t-distributed stochastic neighbor embedding. So this is a nonlinear dimensionality reduction and visualization technique, just as SNE. It maps the data points into a lower dimensional space such that it preserves the distance between points that are close together. So it focuses on preserving the local structure. The results are non-deterministic, so it is based on gradient descent with annealing, so it's not deterministic, and it is still computationally intensive. We're going to discuss about this later, how we can improve the computational time. Okay, so it is important that to note that t-SNE does not produce a transformation or a projection of the space. It generates an embedding into a completely new space. So the transformation is not generic; it's just an embedding of the data. So it's you cannot come with a new data point that wasn't used during the optimization and apply some transformation to obtain its location in the embedding space. So you cannot do that. So yeah, and the features, so another reason for why not use this approach as a dimensionality reduction approach is that the features in the new space are difficult to interpret. so they're not useful for classification, especially because you cannot reproduce this transformation for test data. Okay, so the idea with t-SNE is to change the Gaussian distribution in the embedding space, so the distribution for y, from a Gaussian distribution to a Cauchy distribution, and this is shown to solve the problem of data having so yeah, if you sample, for example, data from a Gaussian distribution in the ball of radius, let's say of radius 1, so in the unit ball, as you increase the dimension of your space, the distances, if you compute the distances between points, you will see that most of the points will tend to cluster or to to get sampled near the ball surface, and the distances will be grow very much between the data points. So as you increase the dimension, the distances will increase exponentially. So this happens with a Gaussian distribution, and because these distances grow in this unit ball, even if you use the Gaussian distribution, which disregards the data points that are very high from the mean, you will still have very high distances between points that are close together. So in order to solve this problem, you can use a Cauchy distribution in the embedding map, and the Cauchy distribution is a t student distribution with 1 degree of freedom. So the name of the approach, t distributed SNE, comes from the fact that we changed the distribution of the embedding map. Okay, so the approach was introduced in 2008, so it's slightly more recent. So the main difference is to change the distribution of the embedding map. So what does this mean is we replace this this old distribution, which is the Gaussian distribution of so the Q of I and J. So this was the density probability of the embeddings, with this new density probability that is computed as follows. So instead of using the exponential here, we use 1 plus actually it's 1 minus the difference between the distance between pairs of points, and this is raised to the power of -1. So this is 1 divided by this, actually. Okay, so the algorithm converges something like this. So this example is taken from this tutorial. So if you are interested in t-SNE, I think you should. This is a good tutorial to follow. Okay, so about the gradient interpretation. So since we updated here the density probability of the embedding, the gradient now has a different different formula. So the gradient of the objective with respect to the embeddings y that are optimized during the process. And here we have visual interpretation. So this component of the gradient, so the difference between two data points, can be interpreted as a spring, and this other component controls how compressed or exerted is the spring between these two data points. Okay, so here we do a sum. So we choose for each point y, so the gradient with respect to the point y is equal to the sum of all the other data points. So here we consider actually all the springs of this data point with respect to all the data points here. And of course, if we consider the time complexity, so if we compute all the gradients with respect to all the data points, then the complexity is squared, is the squared n, where n is the number of data points. So still, t-SNE is computationally intensive, is limited to data sets with only a few thousand of points. But it still provides better visualization. So here we apply the data set on 5,000 samples of images from the UCI optical recognition of handwritten digits data set. And you see with PCA you obtain this projection, and most of the classes are mixed together. You will find some classes that are farther apart, but still here t-SNE is better at separating these classes, so it provides better visualization of the data set. Okay, so we also have an approach, a version of t-SNE that is faster, that can be computed much faster. So this is just an implementation, so it is also called the Barnes-Hut implementation. So it is the same objective as t-SNE, but it reduces the time complexity to n log n. So because of this change, it scales to a larger data set. It reduced and it is based on reducing the number of pairwise forces that need to be computed. Okay, so the idea behind the algorithm is that forces that are exerted by a group of points that are relatively far away are all very similar. So the points are all far away and also packed together. So the idea with t-SNE is to use a Barnes-Hut approximation of these springs. So instead of computing all these springs independently, we represent all these data points to only one spring. So this is represented using a single interaction. The solution here is actually based on implementing a quad tree, which divides the space into these regions, and then we compute springs. So all the points in one region will form only one spring. Okay, and here with this optimization, we can apply Barnes-Hut SNE on all the 70,000 MNIST images, and we obtain this visualization. And it improves the running time from days to about 10 minutes. So this speed improvement from n squared to n log n is quite important. Okay, so we can apply also, it is interesting to apply SNE on embeddings of models on and to see if they provide any meaningful visualization. So in this case, if we apply t-SNE on AlexNet embeddings you'll find that the images that correspond to these embeddings cluster nicely together into this nice visualization. Okay, so the idea is just to take the last layer of before the classification layer of AlexNet, and you obtain these visualizations. So for example, in this area you'll find flowers that are actually or plants, yeah, that are visually they are correlated together. So it means that the embeddings are obtained by AlexNet are meaningful and have a nice visual interpretation. Okay, so this is just an example on how you can use t-SNE to visualize, let's say, neural networks and also other models. And this was the last slide of my presentation. So let's go back to the chat and see if there are any questions. Okay, so there is a question if there is a limit on the number of features in the new space. If this refers to PCA, the number of features is the same as the original space. They are only different, so they are sorted in decreasing order of variance. And for t-SNE, as I said, we usually use 2 or 3 features. I think there is no restriction, but the only use of the algorithm is to visualize the data. So you do not want to do it in a higher dimensional space. It wouldn't have any you would not have a reason to do it in more than 2 or 3 dimensions, because this is just a visualization technique. So if you try to reduce to a higher dimensional space, then you will not be able to visualize the data. And you cannot use it as a dimensionality reduction technique because it doesn't generalize. So it doesn't learn a transformation, it just projects the data points that you give it. So it's not applicable on a new test data that is not seen during training. So unlike PCA, it doesn't give you a transformation as output that you can apply a new data. It is just an embedding for the data set that you give as input. Okay, so yeah, are there any other questions about these approaches? Just write them down, and I'll take them in the order they appear on screen. Okay, so you can use t-SNE as a data visualization technique. Of course, you can use it, but do not try to use it for dimensionality reduction. So perhaps you might want, if you want to do your second project on visualization, perhaps you can compare maybe PCA with this as a visualization technique, and try, I don't know, different hyperparameters and so on. So you can use it if you want to go into this direction. Okay, so I think there aren't any other questions. So thank you guys for participating. And yeah, I'll see you at the presentation. I will provide some information prior to the presentations on 25th of January. And yeah, see you then. Okay, thank you and bye bye.